Welcome to the Tiny Talks Algorithm and Tools. We're going to have 4 exciting presentations. We'll start with David SAWYER, who is a Canadian tech entrepreneur and co-founder and CPO of DeepLight, a Montreal AI software startup. Davis, you can start.
Excellent. Thank you so much, Joseph, and thank you everyone for joining this session. We're very excited to share DeepLight Neutrino, which is very much a tinyML algorithm and tool, and how it can enable automated constrained optimization of models. So thank you very much for joining this session, and let's dive into things here. So very quickly, we only have a few minutes here to kind of go into some very exciting topics, and there's been a lot of really cool stuff talked about all week and a few general themes here. So we'll stick to the heart of the matter. But basically, we're going to go through a quick background on what optimization really means in this context and what specifically we're trying to optimize, how this toolchain DeepLight Neutrino can enable this type of optimization, really model optimization in this case, look at a few use cases, some kind of hallmark or marquee tinyML applications these days like wake words, and then wrap up with some conclusions and questions on future directions. So let's dive into it. Very quickly at DeepLights, so we are very much focused on the deep learning side of things, as the name implies. We're proud to be the local chair for tinyML Montreal, which is kind of like a ground zero for a lot of things in deep learning. We're doing a tremendous amount of research and development and productization of tinyML across the automotive, manufacturing, and of course in the low power semiconductor space as well. So for today's talk, very kind of famous chart nowadays in our space, but the whole motivation here is that we have all these awesome deep model architectures that can provide pretty sophisticated level of predictions, and in the pursuit of better accuracy, of course, they're getting deeper and deeper. And really, when we talk about optimization, as we try to bridge the gap from how crazy complex these models have got and where we're at from a semiconductor side of things, of course, great theme from this topic as the talk series has been domain specialized architectures, how we can do very interesting, sophisticated tasks with incredibly low power silicon, which is great. And at the same time, kind of coming from the other direction, it's okay, well, how do we solve this fundamental issue of big, deep, intensive, over-parameterized models in the first place? And really, in this topic and this tool chain, we're going to focus on algorithms that really do this level of optimization. How can we take some model content? How can we take some platform descriptions and achieve meaningful levels of optimization at the model level prior to deploying on the silicon to bridge the gap that a lot of topics, a lot of conferences, a lot of research has identified these days. And the way things look now, again, a lot of interesting algorithms and proposals coming up in this talk series. And I think a really underrated thing is how complementary a lot of these types of optimizations are. So how this looks, which should be no surprise to anyone, is you're training in typically your cloud environment using these standard frameworks and maybe some hyperparameter optimization, which is one level, of course, handing off this model to what really is often kind of a la carte way of optimizing things. We have different proposals, different techniques. Some work well with others, some don't. And really, we're trying to look at this level 2 today and say, well, what tools and more specifically, kind of paved ways can we get through this level 2 and bridge the gap to level 3? Even in some cases, looking at well-known models like Resident 50, even with a good level of optimization from some traditional pipelines, we're still not quite there in terms of the compute profile and resource profile that we may want to be for a lot of applications. And I think just to bridge on something that was brought up in the panel just before this talk is, having paved ways to do some of this stuff is really going to have a floodgate or open up a floodgate on applications, devices, shipments, all that kind of stuff. So this level 2 here is really something we're going to focus on in this talk and say, can we do more here? Can we do more at the model level prior to going to the low level optimization and compiler level? And how can we have a tool chain to do this, an automated tool chain? That's really an important part of Neutrino. And more specifically, because we're talking about tinyML, of course, we can automatically optimize for maybe better throughput, or we can try and reduce latency on high power hardware. Really, we're talking about making networks as small as possible because size is really the big challenge. We're talking about the very edge, the very edge of computing, sensor edge, which is of course tinyML's home. So name of the game is we have some networks, we have some deep learning models which have good accuracy. How can we create tool chains and algorithms that really bring them into this caliber of compute profile. So size is the biggest challenge here. And again, a bit of maybe preamble here, but it's really not just about compression. I know we're often reporting things like size in bytes or changing the bit precision or data type, or trying to do some kind of smart compression schemes. I think design automation is really an underrated thing in the tools and algorithms component of doing tinyML. Of course, it's a subsystem within many subsystems that deliver some intelligence. But design automation from a experimentation and productization perspective is really the goal here. Instead of spending hours, weeks, months to create these fine handcrafted models, which can often themselves be suboptimal, really we're trying to do a three-step process here. Start from something large and accurate, receive some constraints, and provide a low code, or at the very least, low friction method toolchain of providing an automated, optimized network that meets those constraints. It's not just about compression, it's really design automation. That's kind of one of the pursuits here. And so how does this look? Since about 2019 and in the last year, we've made available our Deeplite Neutrino software, which does exactly this. It really take a network you've made and enable some intelligent trade-offs to be made as dictated by a human operator. So an AI engineer or expert is really using this software to go through different trade-offs they'd like to make that would otherwise be manually infeasible or manually impractical to solve. So at a very high level, how this looks is input is a network and some data set. The configuration are these different KPIs and modes and trade-offs that you can make. Again, all about trade-offs. And then at the other end comes some optimized network. That's really, we're going to go into the inner workings of this in a second, but that's really the tool here, is a tool to take this big network, allow some trade-offs, and then at the other end, get the compact network. And of course, there's various complementary approaches to do this. There really doesn't seem to be one kind of golden algorithm or one golden tool at this point. It's really a mix of some innovative stuff and some clever engineering to try and have an effective tool. That's the name of the game. So how does this look in action? So what Neutrino can do and what the automation really provides is a way of specifying the typical inputs you have for any kind of deep learning or AI deployment. Just pause here a second to see what the inputs look like. Starting from a data set, this can be a custom data set, custom annotations, but in this case, we'll use something simple. It could be your model. So again, using a well-known model, VGG, but could be even customized models with custom loss functions and things like that we can talk about. But any model topology will do as long as it's CNN based. Accuracy drop is first and foremost here. So we want to be able to preserve accuracy and the functionality of the model within the criteria directed by the user. So this is a hard constraint. It's something fed to the engine and said, respect my accuracy criteria with whatever you do in your compression or optimization side. We have a couple other controls, and more expanding into the software at this point. But really, that's the level of effort required from the user. Once this is inputted, you simply press run, and a couple interesting things happen. First, the model is profiled. What that means is we want to get the evaluation metric, in this case accuracy. We want to get the initial size in full precision, count the max, count the parameters, memory footprint, etc. And this is all done using a piece of code called our profiler. We're actually making that open source kind of at the beginning of April, which is exciting. I'll talk about that in a second. But once it's profiled, the engine comes up with a estimation of how long the job should take. In this case, it's saying about 2.5 hours to meet this accuracy criteria, which is the 1% drop we saw earlier. And as this engine runs, it terminates in basically an optimized model. And so what we've seen here is instead of many heuristic-based or intensive processes to kind of handcraft or tune these networks, in 2.5 hours in a fully automated pipeline, what we've done is taken a model that was 76 megabytes, reduced it to 2.7 megabytes here, as you see here in full precision, reduced the MAC from about 400 million down to 75 million. So a significant reduction there. The parameter reduction is linear with the size. We're reducing parameters here by 28x as well. And the memory footprint is drastically improved. Now, again, this is a compression task. You want to take big model and make it as small as possible. Of course, in this same tool chain, we have other objectives, such as Neutrino has what's called a latency mode. That's more for optimizing the speed of the model on high-profile hardware, high-powered hardware like GPU, CPU, Intel CPU. But in this case, we want to compress, we want to get as small as possible to bring the model size as close to the edge of computing as possible. And then what comes out the other end here is this optimized Onyx graph, which can be output to all the different tool chains or compilers. Same story for TensorFlow Keras. If I'm putting a TF Keras model, we can output TF Keras to the other end. That's really it. So what's happening here, to give a little bit of idea of the innovative stuff, is really approximating these networks that are big, that have large layers, and using this intelligent design space exploration, this tool chain, to come up with smaller series of networks or series of layers that approximate this initial network. That's very non-trivial and really requires some intelligent way of reducing the search space, manipulating the network, parsing the graph, all that kind of cool, fun stuff. To give you an idea of the effectiveness of this approach and tool across different networks, here are some well-known networks with some different compression rates. Again, all in full precision. This is before we're doing anything like quantization or compiler-based optimization. The idea of this toolchain here is to produce compact models in the first place while maintaining accuracy. And that's, as you see from this column here, this is always within direct control of the user under this tool paradigm. So what can we do with this, I think, is the natural question. So again, it's been talked about a lot, and I think putting the kind of the raw numbers on ice for a second, it's really about the automation and workflow here, the workflow simplification. I've worked with a great partner called Andy's Technology, RISC-V CPU vendor out of Taiwan. Published some of this results publicly in some of our academic papers and also press releases with the company. Really exciting stuff when you consider, and I think this is a general theme of the conference, how low can we go while maintaining good accuracy here. And so this is an exciting case where we saw meaningful reduction on an already compact use case for commodity hardware, an upcoming RISC-V CPU. And on the other side of the equation, retrofitting, I think, is a really cool thing for tinyML. We have a lot of existing solutions, a lot of existing hardware. One of our customers, for example, is using GPS-based detection, but like many things, GPS is not always up to date, the fastest, most adaptive way of recognizing the environment. So moving to a camera-based approach for speed limit recognition without upgrading the hardware, which is key here. So we're excited to say that we're able to achieve this, and this is a very stereotypical use case for how Neutrino is used today. And one kind of general takeaway as we get into the conclusions here and kind of wrap up is done a lot of experiments on a lot of existing networks. This is by no means meant to be a whole exhaustive list of networks here, but a couple interesting takeaways here. If you look at models from like the...
Again, just a quick shout out to our sponsors. Bear with me for 1 minute. We have different categories. We have executive sponsors. First one being ARM. Then we have Qualcomm. We have Samsung. Platinum sponsors. ADA Compute. Lattice Semiconductor. Gold sponsors. BrainChip. Babel Labs. DSP Group. Edge Impulse. EMSA. Gray Matter Labs. Greenwaves. Himax. Imagimob. Latent AI. Maxim Integrated. Quixo. Reality AI. SensiML. Silicon Labs. Sentient. Google TensorFlow. XMOS. And lastly, silver sponsors, Edge Cortex, Hotchi, and Synsense.